My name is John. I'm a postdoc at the University of Maryland in the Public Health Aerobiology Lab, and I'll be sharing some of our initial results on our ongoing project looking at bacteriophages, surrogates, and eukaryotic viruses in both liquid and aerosol test chambers. I'll start with a quick introduction and our objectives for the project, as well as where we're at, followed by the current methods that we've employed and our initial results and some comparisons to previous literature results, and then follow up with our ongoing work. So there's an increased interest in UV use as an airborne pathogen disinfection, as well as increasingly more commercially available technologies for UV disinfection. As you guys know, 254 is already known to be well effective for control of airborne microorganisms. So some example references. But its use is limited to upper room air disinfection for safety reasons, whereas 222 is considered generally safe for whole room air disinfection, but could benefit from more efficiency studies to increase acceptance. Now, viruses can be readily used for such efficiency studies in controlled environments, but it's not so acceptable for use in occupied spaces due to the health risks associated with them. Therefore, phages might be an appropriate use case for aerosolizing into occupied spaces for real-world efficiency studies. So the objective is to determine 222 nanometer UV inactivation dynamics for phages in comparison to viruses for use in aerosolization experiments. And to accomplish this, we look to replicate the liquid-based done previously in our labs, using 4 phages that we have available, T1, T4, MS2, and 56, as well as to compare this with lab available viruses, such as we have a known well-characterized strain of influenza that the lab at the Public Health Aerobiology Lab uses quite frequently. To then transfer this knowledge and experience into doing controlled environment aerosolization experiments in both a single pass flow tunnel system as well as a chamber system that is developed by some of our engineering colleagues at UMB, also at the University of Maryland. And then this would allow a comparison between liquid dynamics and aerosol dynamics between both virus and phages. And then we can look at the results of that and determine what phages could be used for best comparison against eukaryotic viruses in real-world cases for hopeful aerosolization in both occupied and unoccupied real-world environments. So currently we're just at this step 1, looking at replication of liquid-based experiments in health, where we only currently have some results regarding MS2 inactivation in liquid. And this method includes the use of a open lumen-based chamber with a 222 nanometer UV light source. And what we do is we split a MS2 phage stock that's diluted in a phage buffer into 2 separate plates, one of which is destined to be exposed to UV and one of which is set aside simultaneously for incubation, not UV exposed, so we can compare unexposed and exposed. And we have an example of what it looks like on the right there with the UV light on and the petri dish at the bottom. For quantification of viable phages, we use the soft agar overlay method, and this is initially done the same day of the exposure event, where we do a spot test to give us a very broad idea as to what dilutions we have to use. When we do a plaque assay for more specific quantifications to save us time and resources. So I've included examples of the plates that we see. This is all done in triplicate, and we do each experimental exposure in triplicate as well. And so this is an example of our results so far. So we only have 4 points that we've used for MS2 so far in liquid, and we have between about a little bit less than 10 to above 90. And we see a max reduction of about 6 log. So this fluent was determined using potassium iodide actinometry, and we have a formula derived from these 2 papers. And so you can see this absorbance over time curve that we generate, and we have a max absorbance that is going to be slightly above 2. And we use this formula to generate the fluency. This was confirmed using the fluence on this table is the fluence calculated from the absorbance of the actinometry solutions versus the 2 radiometers that were also used over different times. And you can see where the actinometry actually maxed out for the absorbance at the bottom at 10 and 20 minutes, where it looks the same, whereas it continues growing with the radiometers. So our MS2 results currently show something different from what's previously reported, such as with monotel and oetel, where they reported higher inactivation rate constants. Some thoughts as to why this might relate to the setups, where we have, for example, on the far left of this slide, oetel had a UV lamp above and below their petri dish. But the monotel had a much more similar setup to ours, where we have our lymphatic in the middle, where even their distance between sample and the lamp was much similar to ours as well, so it's kind of unknown if that was the reason. It could be also media. As I mentioned, we use a phage buffer solution, whereas they use a PBS. Or it could also be the max fluids, where when we align ours, it would be similar to what theirs were reporting. They had more time points, and they had cut off their dose or fluids earlier than ours did, whereas we expanded further but had less time points, so we'd be biasing our curve. So for our ongoing work, we have to do more UV dose tests, so have more time points to analyze. We want to incorporate digital PCR for total phage concentrations, and obviously include 5, 6, 2, 1, and 4 to be testing the liquid, as well as doing influenza liquid tests. And then following our collaborators' completion of the single pass tunnel system, we have to do the associated phage and influenza aerosolization tests as well. And then we have to evaluate the UV effects of Bacteriophages in a large chamber that they also have available. And then finally, using this data to inform us as to what phage we can use to replicate eukaryotic viruses in an potentially occupied room with UV on and off. So I'd like to thank the Public Health Air Biology Lab group, as well as the City at UMB Engineering group, and the Balby Funds for their funding.